Now based on the concepts what we learned till now, just we will solve few problems on our waveguides. Problem 1. An electromagnetic wave propagating in an air-filled 10 by 4 cm waveguide has its electric field in phasor form given as Ez is equals to 5 sin 20 pi x sin 25 pi y e power j beta z volt per meter. What is the mode of propagation of the electromagnetic wave? Option A TM21, option B TM12, option C TE21, option D TE12. Just to observe the type of waveguide which is given to us, it's a rectangular waveguide with dimensions 10 by 4 cm. The rectangular waveguide has a broader dimension of 10 cm, narrower dimension of 4 cm. So A is equals to 10, B equals to 4. Remember that. And Ez is given to us. Recollect, if Ez is given to us, clearly it is a TM wave. It is not TE wave, TM wave. So you can eliminate two options which are corresponds to TE. Right? The TM are left for us. Right? Now, for a TM wave, what is the wave model? What is the wave equation we have? Ez is equals to C sin m pi by ax sin n pi by by e power j beta z. Here it is given, and it is omega t minus j beta or j gamma. That what we have, right? Or j omega t minus gamma z, whatever it may be. Different time variations and propagation constant terms will be there. So if you compare that one, a similar type of equation is given to us. So C, instead of C, 5 is given to us, that the magnitude is 5 sin m pi by a. Instead of m pi by a, what we have here? M pi by a is equals to 20 pi we have. Just keep it aside. And here it is n pi by b. Instead of n pi by b, here we have 25 pi. Just you take these two. M pi by a is equals to 20 pi, n pi by b is equals to 25 pi. Right? Now substitute this a is equals to 10. That is m pi by 10 is equals to 20 pi, and here it is n pi by, here it is what is b? B value is just 4. So 4 is equals to 25. Right? Now after simplification, what you will get here? M is equals to 200, n is equals to 100. Now what we require is the type of mode. Get the ratio of these two, m is to n we get. So m is to n is equals to 200 is to 100, which is equals to simply 2 is to 1. So the type of wave what we have is TM wave, and the mode is 2, 1. So clearly you are supposed to observe that it is a TM wave with mode 2, 1. So clearly this option exists in our option A. That is option A is correct answer. So option A is the correct answer. For this, clearly once again identify the type of wave which is given to us. As Ez is existing, it is TM wave, and the remaining analysis is purely depend upon the past discussion that what we have. This is the simple solution for this problem. Problem 2. The electric field component of an electromagnetic wave propagating in a rectangular waveguide is given in phasor form as Ez is equals to E0 sin 50 pi x sin 40 pi y e power minus gamma z volt per meter. The ratio of field components Ex to Ey is option A 1.25 cot 50 pi x tan 40 pi y, option B 0.8 cot 50 pi x tan 40 pi y, option C 1.25 tan 40 pi x cot 50 pi y, option D 0.8 tan 40 pi x cot 50 pi y. Now clearly observe what is the data given to us. For this particular problem, Ez is given to us, and he asked to obtain what is the ratio of Ex to Ey. Since Ez is given to us, immediately recollect that it is a TM wave, transverse magnetic wave. For TM wave, what about Hz? Hz is equals to 0. After substitution of Hz, definitely you will have equations for Ex and Ey. So try to recollect that Ex equation is there. Put Hz is equals to 0 and try to write down its equation for Ex. What is the equivalent equation for Ex after putting Hz is equals to 0? Simply minus gamma by h square dou Ez by dou x. Minus gamma by h square dou Ez by dou x. So substitute Ez here. Similarly, what is Ey? Ey is equals to minus gamma by h square dou Ez by dou y. So this is the equation for our Ez. Now Ey, just substitute Ez here and obtain Ex and Ey. So which is equals to minus gamma by h square dou Ez by dou x. So what is dou Ez by dou x? With respect to x, differentiate this one. What I do is I'll ignore the terms which are which can be kept constant for both x and y. So ignore this E0, ignore this e power minus gamma z, just you consider only these two parameters which are sufficient for us. I can ignore this minus gamma by h square also, because this gamma by h square is common to both, right? So keep them aside. Now with respect to x, if you are differentiating with respect to x, what we will get here? Cos 50 pi x, and the internal differentiation is 50 pi, and this sine 40 pi y left for us. And once again, as all these are not important for us, just I am ignoring it, okay, which is equals to, here this term can be written as minus gamma by h square. This is with respect to y, right? So the first term remains as it is, sine 50 pi x, and for this one what you will get is 40 pi as the internal differentiation, and it is, as this is sine, you will get cos 40 pi y. So the remaining terms can be left. Now what is the quantity we require? Ex to Ey, just you take the ratio of these two. If you are taking the ratio of these two, that is Ex by Ey is equals to, this term will be vanished, cos by sine, cot. So simply it is cot 50 pi x, and sine by cos, tan, that tan 40 pi y. Pi will be cancelled, 50 by 40, it's a 5 by 4, approximately 1.25. So this is the answer that what we require. This is available in option A. Just you consider our Ex, Ey equations as our component is Ez, z is equals to 0, that is clearly this is a TM wave. After that one substitution and solving, then you will get this equation, this answer, this is option A is correct. Problem 3. An A by B air-filled rectangular waveguide is operating at a frequency f is equals to 5 GHz. What will be its dimensions if the design frequency is 10% larger than cutoff frequency of dominant mode, while being 10% lower than the cutoff frequency for the next higher order mode? Option A equals to 3.3 cm, B equals to 2.7 cm. Option B, A equals to 1.1 cm, B equals to 0.9 cm. Option C, A equals to 0.37 cm, B equals to 0.3 cm. And option D, A equals to 0.5 cm and B equals to 0.4 cm. Now clearly observe what is the data given to us. Here A by B is a rectangular waveguide that what we have is operating at a frequency of 5 GHz. This is the operation frequency. And he mentioned that clearly the operation frequency is 10% more than the dominant mode cutoff frequency, and it is 10% less than the next higher order cutoff frequency. So what we are supposed to do is, we are supposed to compare this 5 GHz with its dominant mode cutoff frequency and next higher order mode cutoff frequency. So for this, what is the cutoff frequency of TE10 mode and what is the cutoff frequency of TE01 mode we require? Now what is the basic formula for cutoff frequency? Fc is equals to, this is the equation for Fc. Now what I have to do is just I have to obtain the equations for cutoff frequency of TE10 and TE01. Now the cutoff frequency Fc for TE10, m is equals to 1, n is equals to 0. M equals to 1 I will substitute here, n is equals to 0. N is equals to 0 means this term will be vanished. If I substitute m is equals to 1 by a square, this will becomes a. Just it becomes simply c by 2a. Similarly, what is the cutoff frequency of TE01? TE01, if you substitute 0 here, it's a 1 by b square, b remains for us, this is c by 2b, right? Now this is the cutoff frequency of our TE10, this is the cutoff frequency of our TE01. Now as per our problem, this f is equals to 10% more than f TE10. So here it is our 5 GHz, 5 into 10 power 9 is 10% more. 10% more means if you are taking the 100 as the cutoff, 10% more means 1.1. The percentage is 1.1 times of our c by 2a, 10% more than or C by 2a. Similarly, it is 10% less. So this is 5 into 10 power 9. The 5 gigahertz is 10% less, means then 90%. 90% is 0.9 times of C by 2b. Just you can solve these two. C is nothing but the free space or the light velocity in free space. Since the waveguide which is given is a air filled waveguide, I am considering this one as C. So substitute C is equals to 3 into 10 power 8 meter per second or 10 power 10 centimeter per second. That's better. Here also it is 3 into 10 power 10 centimeter per second, and bring this B to the left hand side, bring this A to the left hand side, and take a calculator and solve this one. Then you will have solutions for this A and B. From this one, A is equals to simply 3.3 centimeter and B is equals to approximately it is 2.7 centimeter. From these two are the dimensions for a rectangular waveguide. These two are available in our option A. So option A is the correct answer. Problem 4. A rectangular waveguide of internal dimensions A equals to 4 centimeter and B equals to 3 centimeter is to be operated in TE11 mode. The minimum operating frequency is option A 6.25 GHz, option B 6 GHz, option C 5 GHz, and option D 3.75 GHz. Observe the data given to us. Here a rectangular waveguide of dimensions 4 cm, 3 cm are given to us, and it is operating in TE11 mode, and we require the minimum operating frequency. Minimum operating frequency means cutoff frequency. So what is the formula for cutoff frequency of our rectangular waveguide? Fc is equals to C by 2, and until and unless mentioned, clearly remember that the waveguide is filled with the air. That's why it is a air filled rectangular waveguide. That's what we are assuming. That's why here I am writing that this one has C. Otherwise, you are supposed to write down that is 1 by under root mu epsilon. Remember that point. C by 2 square root of m by a whole square plus n by b whole square. So which is equals to, since the answers are given in our all the dimensions are given in our centimeters, write down this one also in centimeters. 3 into 10 power 10 divided by 2 square root of, what is m here? TE11 corresponds to m value is 1, m is equals to 1, n is also equals to 1. So 1 divided by, what is a is equals to 4 centimeter. So 1 by 4 square plus, here also it is 1 by 3 square. The broader dimension is 4, narrower dimension is 3. Now take a calculator and simply calculate this one, then you will get an answer of 6.25 gigahertz. This answer is available in option A. So option A is correct answer. Problem 5. An air-filled rectangular waveguide has inner dimensions of 3 cm by 2 cm. The wave impedance of TE20 mode of the propagation in the waveguide at a frequency of 30 GHz is option A 308 ohms, option B 355 ohms, option C 400 ohms, and option D 461 ohms. Now observe the given data. Here a rectangular waveguide with dimensions 3 cm by 2 cm is given, and it is operating in a mode of TE20 mode and is operating at a frequency of 30 GHz. We require the wave impedance. So what is the simple formula for wave impedance? Just write down the formula for wave impedance. Zt is equals to eta naught divided by under square root of 1 minus, so what is the formula for that one? In terms of frequencies I am writing. So 1 minus Fc by F naught whole square. In terms of lambda also you can write, that is lambda naught by lambda c whole square, where eta naught is the intrinsic impedance of the free space, approximately it is equals to 377 ohms. Remember that one. Now here to substitute, eta naught is known to us, F naught is operating frequency which is given to us. So what is the cutoff frequency? We are supposed to calculate the cutoff frequency again. So Fc for which mode? TE20 mode. So m is equals to 2, n is equals to 0. Substitute it one. C by 2 square root of m is equals to 2. 2 divided by, what is the broader dimension of that one? M by a is 3. 2 by 3 whole square plus 0, that what we have. So 2 will be cancelled, that simply it becomes c by 3. C is nothing but the velocity of light, which is equals to 3 into 10 power. Here the dimensions are given in centimeter, so 10 power 10 I am considering. So the answer which is left for us is 10 power 10 Hz. So the cutoff frequency is 10 power 10 Hz is nothing but 10 GHz. right? The cutoff frequency is 10 gigahertz and the operating frequency is 30 gigahertz. That is, FC is available, F0 is available, eta naught is equals to 377 ohms, and substitute all these things, then approximately the intrinsic impedance, it's not intrinsic impedance, wave impedance. The wave impedance for TE20 mode is approximately what you will get is 400 ohms, and this is available in option C. So option C is correct. Problem 6. A rectangular waveguide having TE10 mode as dominant mode, having a cutoff frequency of 18 GHz for the mode TE30. The inner broad wall dimension of the rectangular waveguide is option A 5 by 3 cm, option B 5 cm, option C 5 by 2 cm, and option D 10 cm. Now clearly observe what is the data given to us. A rectangular waveguide has TE10 as dominant mode, and it is operating at TE30 mode, has a cutoff frequency of 18 GHz. For TE30 mode, the cutoff frequency is 18 GHz. So what is the broad wall dimension? That is, what is the broader dimension of our rectangular waveguide? For that, take the cutoff frequencies FC for TE30 mode. For TE30 mode, so what is the equation? C by 2 square root of m is equals to 3. So it is 3 by a whole square plus n is equals to 0, corresponds to 0 here. So which is equals to simply C by 2 multiplied with 3 by a. C by 2 multiplied with 3 by a. FC is available with us. What is FC is? 18 into 10 power 9. That's 18 gigahertz, which is equals to C is 3 into 10 power 10 centimeter into 3 divided by 2 into a. Just bring this a to the left hand side and this entire term to the right hand side, then you will get the broader dimension of our rectangular waveguide. After simplification, what you will get is a is equals to 5 by 2 centimeter. This is available in option C. So very simple problem. The answer is option C. Problem 7. A rectangular metallic waveguide is filled with a dielectric material of relative permittivity epsilon r is equals to 4, has the inner dimensions 3 by 1.2 centimeter. The cutoff frequency for the dominant mode is option A 2.5 GHz, option B 5.0 GHz, option C 10.0 GHz, and option D 12.5 GHz. Now observe what is the data given to us. A rectangular waveguide of dimensions 3 by 1.2 centimeter is given to us. Here A is equals to 3, B is equals to 1.2 centimeter, and it is filled with some other dielectric medium. It's not filled with air, with a relative dielectric constant 4. Now we require the cutoff frequency. As in our one of the previous problems, I said we are not always supposed to take C in the equation of cutoff frequency. Instead, we are supposed to consider 1 by mu epsilon. Now I will write down the equation for that one. So FC is equals to 1 by 2 square root of mu epsilon we are supposed to consider. If it is air filled, 1 by square root of mu epsilon is equals to C. But it is not air filled, it is filled with any dielectric medium. Mu epsilon and square root of m by a whole square plus n by b whole square. So this is the equation that what we are supposed to use. Now this cutoff frequency will be calculated for which mode? Dominant mode. What is the dominant mode in rectangular waveguide? TE10 mode. So for TE10 mode, that is FC for TE10, which is equals to 1 by 2 square root of mu epsilon. M is equals to 1, n equals to 0. This will be cancelled. So 1 by a square, left term is 1 by a. Now instead of mu and epsilon, what you can write? Instead of mu, you can write down mu naught. Instead of epsilon, you can write down epsilon naught into epsilon r. So this can be once again modified as 1 by 2 square root of mu naught epsilon r divided by a. Simply it's into a in the denominator. So which is equals to 1 by square root of mu naught epsilon naught can be written as c. So this can be written as c by 2 square root of epsilon r into 1 by a. Now observe, everything is available with us. C, the velocity of light is available. 2 epsilon r, that is the data which is given to us. 1 by a, 1 by 3, substitute them and take a calculator, and if you calculate this one, what you will get is approximately 2.5 gigahertz. GHz as the answer. So this 2.5 GHz is available in which option? Option A is correct. Problem 8. Consider a rectangular waveguide of internal dimensions 8 cm by 4 cm and assuming that H10 mode of propagation, the critical wavelength would be option A 8 cm, option B 16 cm, option C 4 cm and option D 32 cm. Here is a very simple problem. What is the data given to us? A rectangular waveguide of dimensions 8 cm by 4 cm. We require the critical frequency or the cutoff frequency, whatever it may be. The notation is lambda c. Now we are supposed to calculate this lambda c. If you remember the formula for lambda c, no problem, directly you can use that one. Otherwise you can calculate fc and from that fc obtain lambda c. Directly I will take the equation of lambda c. What is the equation of lambda c? Lambda c is equals to 2ab divided by square root of m square b square plus n square a square. This is the formula for our lambda c. Now the cutoff frequency which is applicable for which mode? For the dominant mode. For the dominant mode, so what is the equation for this one? Lambda c for TE10. For TE10 which is equals to 2ab divided by square root of, so m is equals to 1, so n is equals to 0, this term will be vanished, m square b square, that is the term which is left for us. So m square is equals to 1 square, that is also will be vanished. So b will be cancelled, so it is simply 2a. So lambda c for TE10 mode is 2 into a. Blindly remember that one. Whenever we are taking a rectangular waveguide, the cutoff wavelength for a rectangular waveguide is twice of the broader dimension, 2 into a. So what is 2 into a? 2 into 8 cm, which is equals to just 16 cm. This 16 cm is available in your which option? Option B is correct for this problem. Problem 9. A standard air-filled waveguide has inside wall dimensions of A equals to 4.755 cm and B equals to 2.215 cm. At 12 GHz, it will support option A TE10 mode only, option B TE10 and TE20 modes only, option C TE10, TE20 and TE01 modes only, option D TE10, TE20, TE01 and TE11 modes. Now observe what is the problem given to us. In a rectangular waveguide with these dimensions, the operating frequency is 12 GHz. It is operating with this frequency. Now we are supposed to observe among these 4 modes which one will or all these will exist or not, right? For that the simple technique is among these 4 try to identify the maximum mode, higher order mode. Calculate the cutoff frequency for that higher order mode. If the cutoff frequency is less than our operating frequency, then it is obviously as operable, right? Clearly among these 4, TE11 is the higher order mode. So for this TE11, calculate the cutoff frequency. What is the cutoff frequency for TE11? FC for TE11 is equals to C by 2, 3 into 10 power 8 divided by 2, square root of m is equals to 1 divided by A is 4.755 centimeter. That's why here also I am writing 10 square, that I will consider this one into centimeters whole square, plus 1 by B square. B is 2.215 centimeter square. That what I am doing is just I am calculating the cutoff frequency for higher order mode among these 4. So which is equals to, after taking a calculator and simplifying this one, approximately you will get 7.5 GHz. This is the cutoff frequency. So above this cutoff frequency, all the frequencies will be acceptable, right? Since above this cutoff frequency, all the frequencies are acceptable and the operating frequency is at 12 GHz, obviously this TE11 mode is acceptable for our wave propagation. As this is only the maximum value among these 4, the remaining 4 frequencies are also acceptable. So this is a simple technique that what you are supposed to observe. So the cutoff frequency for TE11 is obviously existing. The cutoff frequency for TE20 will exist, 01 will exist and 10 also will exist. So clearly all these 4 modes will exist in our rectangular waveguide, that is available in option D. This is a simple technique. So if you fail to get this one, if this frequency is more than that one, then what you are supposed to do? You have to calculate the individual cutoff frequencies and examine which one will exist. Okay, so in this one all the modes will exist. So option D is correct answer. Problem 10. The cutoff frequency of the dominant mode of a rectangular waveguide having aspect ratio more than 2 is 10 GHz. The inner broad wall dimension is given as option A 3 cm, option B 2 cm, option C 1.5 cm and option D 2.5 cm. So here there is a very simple problem, that what he gave is the cutoff frequency for the dominant mode is TE10 is 10 GHz. What is the inner border dimension? Once again recollect what is the cutoff frequency, which is equals to C by 2, and I am assuming that it is air field. C by 2 M by A whole square plus N by B whole square. M is equals to 1, N is equals to 0. After substitution of this one, what you will get is simply C by 2A. From this one, what is A? A is equals to C by 2FC. So which is equals to, the answer is given in centimeters. That's why I will consider this one in centimeters. C 3 into 10 power 10 divided by 2 into what is the cutoff frequency? 10 GHz. 10 into 10 power 9. Simply it will be equals to 1.5 centimeter. This 1.5 centimeter is available in which option? Option C is correct answer.